welcome everyone to Mark's thesis defense. We're very proud to have Mark present his work. A lot of excellent work he's done over the years here. Mark started during the pandemic, right? What was it, 21, I think?
2020.
2020. Okay, so he went through all the difficulties of the pandemic and he stuck with his research, and despite all of that, he's managed to do some really nice work. And he's also been a great mentor to others in the lab, very reliable source of support and help for students. And so I think we should celebrate that as well. Okay, so without further ado, take it away, Mark.
Thank you, Dimitri, and thanks everyone for being here. I'm very excited to present my thesis on joint deformation and contact reasoning for robot manipulation. So I want to start today with a vision for manipulation systems, and I'll choose Baymax. So Baymax is capable of performing a wide variety of manipulation tasks autonomously. So we can see that he can manipulate cups, dexterously clean up spills, and even carefully interact with humans. And across these tasks, we notice two important characteristics. So first, all these tasks involve meaningful control of contact. And second, unlike many depictions and realizations of robots, Baymax is, of course, deformable. So let's start talking about contact. So contact is central to almost all manipulation. For instance, if I'm trying to clean something with a sponge, the contact that is made between the sponge as it deforms with the plate is, of course, ultimately what determines if I successfully clean the plate. Or if I'm manipulating an object, via sliding or pushing, right? The deforming contact between my robot and the object ultimately determines if it'll move the way that I want it to. So in manipulation, giving our robots the ability to perceive and precisely control contact is thus a crucial component to building performant manipulation systems. Of course, the other notable feature of Baymax is that it deforms. And in particular, Baymax exhibits elastic deformation. So that means when a force is applied, he deforms and then returns to the original shape when the forces are removed. And elastic deformation in robotic systems introduces some interesting opportunities. So first, it enables for gradual force buildup and dissipation, which can help with precise control, as well as making our robots safer to be around. Second, it enables for stable contact interfaces as the contacts can comply to the surfaces. And hence, we already see a prevalence of deformable tools in human environments. And finally, it provides for the opportunity to observe contact, as evidenced by the recent explosion of compliant tactile sensors. So here we see a tactile sensor where it's observing the compliance of the robot in order to reason about contacts. And so overall, deformability provides an opportunity to both observe and precisely control our contact during manipulations. So even if we introduce compliance into our system, reasoning robustly about that contact has certain challenges. So here we have a sponge that we've mounted on our robot. And when we go and we make a contact with the environment, the first challenge is we rarely get direct access to the contact. And instead we have indirect, noisy, and partial observations of that contact, usually from visual or force and tactile sensors. And deformations, meanwhile, result in high dimensional states and complex dynamics. And thus we really need representations and algorithms that are designed to actually handle these compliant contacts. So in this thesis, I'll explore how we can give our robots an explicit sense of contact. We'll start with methodologies that construct representations that make contact explicit, and then seek to learn those representations from multimodal sensing, exploiting that tight relationship between contact and deformation. And then I'll show how we can use these contact representations to enable effective downstream manipulations and ultimately drive behaviors. So I'll be covering 5 projects from my research, split into 2 parts. So in part one, we'll focus on designing and learning contact representations for deformable tools. And in part two, we'll shift our focus to downstream applications and how we can apply our contact. So without further ado, let's get into part one. So many tasks here require the control of contact, in particular between deforming tools and environments. So tasks like scraping, sweeping, and cleaning all involve the contact between the deforming tool and the environment. And in these tasks, imprecise control of that contact can lead to failures. So for example, when I'm sweeping something, if my contact between the deforming bristles and the table are misaligned, we could fail to properly remove the material. So as such, in this part, what we'll investigate is how we can estimate contacts as our tools deform, utilizing multisensory feedback to reason. So several previous works have investigated the estimation of contacts during manipulation. So for example, representing extrinsic contacts as points, lines, or more generally as patches. So here's a representative example. However, this work has primarily focused on rigid objects, and as such cannot address the deformations that ultimately impact our contacts. Other work has focused on contact estimation and control on tactile sensors. But this assumes that we have actually sensing available at the contact interface, which is not true for all the deformable tools we may want to manipulate. So that brings us to chapter one, learning the dynamics of compliant tool environment interaction for visiotactile contact servo. Okay. So in this chapter, we'll define and estimate a set of extrinsic contact features between deformable tools in the environment. And we look to directly enable compliant contact control, such as scraping with a deforming spatula here or sweeping with a broom. So we'll assume that we can observe our system via visual sensing to get a partial point cloud, as well as recover force and torque feedbacks from the robot doing the interactions. And our goal is then to estimate the extrinsic contact. So to capture this interaction, we propose the following representation. We'll first have a binary contact term that reflects if the system is in contact or not. Second, a contact geometry that captures when the contact is happening, or excuse me, where the contact is happening. And we represent this directly as 3D endpoints of the contact line in 3D space. And finally, we have the end effector wrench, which captures how forceful that contact is. So we estimate this contact representation using data-driven modeling. In particular, we'll use a neural network here. So our inputs are encoded together into a learned latent space from which we then can learn to decode our contact features for the robot. And we don't just care about the contact at the current time step, but we also want to reason about how that contact evolves. So we add a learned latent dynamics function, which allows us to condition on robot actions and then predict how the future latent states will be. And then from those future latents, I can now decode my contact features. So with our contact feature dynamics in hand, we can formulate the compliant contact control problem. So given some goal contacts that we want to realize in the environment, we can set up the following planning problem to track those desired goals. So here we're selecting actions that align our predicted contacts to the goal contacts, subject to the constraint that we are in contact at each time step, and that the contacts are following our learned dynamics module. And this planning problem can then be solved using model predictive control, using our approximated dynamics. So we perform several experiments to test our contact servoing framework. So we start with tracking unseen paths with our MPC framework. So here in red is the desired path, and what we see is in blue, our framework is able to precisely track those desired contacts using our tool. Next, we show that we can zero-shot transfer this framework to an unseen tool that has differing geometries and physical characteristics to our training tools. And again, we see that despite the new tool, our object is still able to closely track the desired contact. And finally, we transfer our method to the case of actually scraping a material from the surface. So here, despite the change in the environment, our method can still effectively track those desired contacts, resulting in the effective removal of the material. So we compare our proposed methodology to a baseline that treats the tool as rigid and computes the intersection with the table. And note that unlike our method, that assumes access to the tool geometry. And here on the left, we can see examples of the resulting swept areas. So the goal is in red, and in blue is the actual realized swept area. And what we can see is that while both capture the main regions of contact, the rigid baseline struggles, especially near the boundaries of our desired contact regions. Quantitatively, we also find that our method consistently outperforms the baseline over various desired contact trajectories in realizing them. So in this first chapter, we've shown that we can directly infer contact features of a deforming tool and how they evolve, enabling compliant contact servoing. And our method is not limited just to the tool that we've shown. So here on the left is an example where we used our same modeling framework and contact features to now model a deforming brush here, where we've integrated it into a system that generates language conditioned contact goals. And this was done in a subsequent research project with one of my lab mates. So this is a nice result. However, for some cases like the sponge or even Baymax that we showed earlier, can we still apply this contact representation? Well, the challenge here is that for these more complex deformations, the contact geometries are no longer well described by our relatively simplistic contact features here. So can we make our representations more rich to capture these more complex contacts? And that brings us to chapter 2, integrated object deformation and contact patch estimation from visiotactile feedback. So in this chapter, we'll extend our contact reasoning to handle more complex contact geometries by jointly representing both the deformed geometry and the contacts between a compliant tool and the environment jointly. So similar to the previous chapter, we'll assume access to a partial point cloud of our tool, along with the force and torque feedback at the wrist of the robot. And now we want to estimate the contact geometries during this more complex deformable interaction. However, the challenge, of course, is how do we represent contacts that can take arbitrary shapes or forms? So our key observation here is that the deformation and the contact surface, whatever form it may take, are very tightly linked, right? So the contact is, of course, what causes the deformation, and the deformation is what determines where the contact must be. So our key idea is to jointly represent these two, the deformed shape along with the contact. And to do this, we introduce a new learned representation that we call neural deforming contact fields, or NDCF. So NDCF takes in our multimodal feedback and outputs both the deformed geometry and the resulting contact patch with the environment. And we represent both of these using a learned neural implicit representation. So what that means is for each point in space, in 3D space, we're going to assign a signal value. For geometry, each point is assigned a signed distance, which is the distance from that point to the deformed surface. And for contact, each point is assigned a binary contact label, 1 if it's in contact, otherwise 0. So the advantage of these implicit representations is that they enable for arbitrary resolution representations. They can be approximated effectively via neural networks, and they naturally admit contact geometries of varying shapes and topologies. Once we have this representation, we can recover the full deformed geometry by uncovering what we call the zero-level set of our assigned distance function. So in particular, the deformed surface is then the set of all points where the sign distance to the deformed surface is 0. The contact patch is then the set of all points from the surface of that object where the likelihood of contact is above some threshold that we set. So this adds some structure to our contact prediction, ensuring that the contact lies on the surface of the deformed geometry as we expect. So here we show some qualitative shape and contact reconstructions on our test simulated interactions. So on the left is the partial input, on the right is the ground truth. The second column here is our method, and we have a baseline which just learns to predict both the geometry and the contact patch using point clouds directly. And what we can see is that over a variety of different interactions, our method results in much cleaner both deformed geometries and contact patch predictions. And we especially see that there are less spurious predictions of contact far away from the actual contact surface. So we also demonstrate sim-to-real transfer. So here interacting with several objects from the YCB dataset. And what we see is we're able to still generate realistic predictions of deformed geometries and contacts using real-world feedback from actual sensors. So here we show some quantitative metrics. So first, we notice that implicitly modeling our deformed geometry results in much more accurate predictions, both in a point cloud and a volumetric score. And similarly, our structured prediction of the contact, both in simulated and in real-world environments, results in much better predictions. And here we're limiting our real-world interactions to a particular case so that we can actually get the ground truth labels of contact. Okay, so that wraps up part 1 of our talk. In part 2, we're going to now shift our focus towards downstream applications and how we can actually apply contact to manipulate objects and drive behaviors. So far we focused just where contact reasoning was our primary concern. But of course, in many manipulations, we are actually trying to control and manipulate other objects. So for example, sliding a book or using a tool. So in this second part of the talk, we'll shift our focus to these downstream tasks, and we'll investigate how we can utilize our contact reasoning and representations to try and improve our performance and behaviors. So we'll start with chapter 3, estimating deformable rigid contact interactions for a deformable tool via learning and model-based optimization. So in this chapter, we'll be focusing on non-prehensile manipulation. So this is any manipulation where we don't grasp an object, and where we instead rely on non-grasping contacts to move the object via sliding or tipping or reorienting. So due to the limiting contacts from our hands here, we rely on external contacts with supporting surfaces to be able to then fully control the motion of our object. And this is sometimes called a shared grasp. During these interactions, it's important to model both the object motions as well as the forces acting on the object, as this allows us to guide object trajectories, control force transfer onto the object, as well as reason potentially about the contact modes that the block is taking. So in this chapter, we'll investigate using a deformable tool now to manipulate an external rigid object in a non-prehensile manner. And we propose a joint learning and model-based approach that will predict the motion and the forces acting on the object during this interaction in order to accurately model as well as guide behaviors. So non-prehensile manipulation is important for cases where a grasp cannot be made due to mechanical or task constraints. And as such, there's been a lot of interest in designing systems capable of pushing, sliding, and pivoting behaviors. However, the majority of these methods assume that the whole system is rigid, and so they do not consider the case in which some part of your system is deforming. Some other methods do employ tactile sensing at the contact with the object to guide non-prehensile manipulation. But similar to part one, this is assuming that we have sensing at that deformable contact interface, which is not always the case. So for our proposed method, we'll assume, as in our previous projects, that we have access to the partial point cloud of the tool, and this will give us a signal of the deformation we can use to reason about the contacts. We now also consider the manipulated object, both in its pose and its physical parameters, so mass, geometry, and friction, which for now we assume we know. And our goal here is to estimate several things: how the object will move, as well as the contact forces from the tool onto the object, as well as the contacts that the object has with the environment. And our key contribution here is to exploit our contact representation with the tool to incorporate a physical structure into our estimator. So we'll utilize data-driven modeling to reason about the complex deformable rigid contact, and then use model-based reasoning to infer the remaining external contacts. So we'll start by describing our data-driven model for inferring both our object motion and the tool contact. So our inputs are embedded into a shared latent space here, where we can then again learn a latent dynamics that's conditioned on the robot action in order to roll out our system. From our predicted latents, we then have two output heads. So first is a block motion head that will predict the next pose of the object as the robot takes an action. And from this predicted motion, we can also compute where any contacts with the environment will be for that object, because we assume we know our geometries here. And our second output will directly predict the deformable rigid contact point and force, where here we're summarizing that contact interface as a single point. Now with these predictions in hand, we want to solve for our remaining environment forces. So rather than predict this, we can exploit our domain knowledge to directly solve for those environment forces. So if we assume quasi-static motion, which basically means our objects are moving slowly, as well as Coulomb friction, we can directly solve for our environment forces via the following optimization. So this finds the minimal set of forces such that all the forces that act on the object should sum to zero, which is quasi-static equilibrium, and that our environment forces obey the laws of Coulomb friction. So this allows us to then create a model-based mechanism for directly outputting our environment contact forces. So here are some example predictions from test simulated interactions. We have our ground truth motions and forces are transparent here, and our predictions are opaque. And what we can see is across a variety of different interactions, pushing, pivoting, as well as different geometries and frictions, our model is able to predict realistic forces and object motion. And this is also borne out in our metrics. So we compare our motion estimation to a rigid body baseline, which just assumes that the block is rigidly attached to the robot. And we see that our method consistently outperforms the baseline on predicting how the motion evolves over multiple time steps. And next, we compare to our model-based estimator for the forces to a purely data-driven technique, where we add an additional output from our learn model to predict the environment forces directly. And what we can see is that our model-based technique consistently outperforms trying to fully learn the system. So that shows the advantage of being able to incorporate this physical structure. So in this chapter, we've shown that by modeling our contact directly, we can directly exploit the physical structures in our system and bring them into our algorithm to improve estimation performance, here by enforcing quasi-static force balance. This does, however, of course, rely on some additional assumptions, namely that we have quasi-static motion and that we know the properties of the object that we're manipulating. Okay, next we'll move on to chapter 4, simultaneous extrinsic contact and in-hand pose estimation via distributed tactile sensing. So in this chapter, we'll shift our focus now to prehensile manipulation, which is where an object or tool that we're manipulating is actually grasped. So prehensile manipulation requires precise in-hand reasoning. We care about modeling the object pose for precise insertion, assemblies, and placements, as well as still reasoning about those extrinsic contacts the tool is making to drive tool use or enable extrinsic dexterity. So precise estimation here faces several challenges, including sensor noise and indirect observation, as well as lots of visual occlusions coming from the grasp. So the recent advent of compliant visiotactile sensors has enabled us a useful feedback line for prehensile manipulations. So this is a class of sensors that uses a deforming gel with a small camera that's mounted behind it to observe that gel. And that results in these images shown here in the center that give us direct feedback during interactions. So they provide several forms of feedback. First, when an object is grasped, the compliance of that sensor provides us with local geometric feedback about the grasp and about the surface of the object. And the compliant nature of the sensor also informs external contacts. So both informing where and how contact is occurring as the sensor deforms to the external contacts. Now, the challenge here is that these sensors provide only a very local view of our system, and thus reasoning over that the full state of our system can be very challenging. So in this chapter, I'll introduce my method TACgraph that goes from tactile feedback images directly to object pose and extrinsic contact estimates. So my method has two main components. First, a learned tactile contact representation to capture the local geometries and forces at the grasp. And then a constrained model-based estimator that uses physical constraints to address the locality of our tactile feedback and fully resolve our system. So previous works have investigated the use of tactile sensing for in-hand manipulation, for instance, for performing pose estimation. However, the locality of that sensing means that only small and highly featured objects can often be precisely located. Other work has looked into extrinsic contact sensing with tactile feedback, but these tend to rely on relatively brittle assumptions and have no sense of the object pose during manipulation. And finally, some work has utilized force-torque feedback to both estimate poses and contacts jointly, but they do not incorporate distributed tactile feedback and tend to rely on external wrench sensing, for example, from a second arm here. So now we'll define our method's inputs and outputs. So first, we have tactile feedback from our deformable gel site sensors. Our method can also optionally take partial visual point clouds, but we'll primarily focus today on tactile-only reasoning. And we also assume that we have knowledge of both the environment and the object geometries. And our goal is then to estimate the pose of the object in hand, along with any extrinsic contact point and force that may be present as the robot interacts. And we'll make an additional assumption, which is that our grasp here is elastic, meaning that as the contacts are made, as the object contacts its environment, the object can move in hand based on the deformations of the tool, but we assume it does not slip with respect to the sensor, so that if the force is removed, it'll return to the same rest pose. So now I'll describe the contact representation that we'll construct and learn. So first, we want to reason about the geometries at our grasp. So we learn a tactile depth model that will predict from our RGB vision-based feedback from our tactile sensor, a local contact patch that we can then recover that shows us where the surface of our grasped object is. And this follows the same principles of deformation and contact we've been using in the previous projects. Since another thing is, since I'm assuming here that the grasp is elastic, we only need to estimate this geometry once from our initial tactile observations after we've grasped our tool. We also want signals as to the external contacts. So we estimate two other in-hand quantities. First, the in-hand displacement of the object as the sensor deforms on external contacts, as well as the in-hand wrench, so the force and torque that the grasp is experiencing at the sensor. And we infer both of these from our RGB tactile image feedback. So now we have these contact representation feedback terms along with the object and environment geometries. So how can we then go from this to our object pose as well as the extrinsic contact point? So as we've mentioned, the key difficulty here is that our tactile sensor is very local, and so it cannot fully constrain our solution sufficiently. However, we can enforce the physical structure of our problem, such as geometric consistency, non-penetration, and the kinematics of contact, in order to reduce the solution space dramatically as we observe. And each of these physical constraints forms a factor which relates some subset of our observations to some subset of the variables that we're solving for. So we'll now look at how these factors can help us actually estimate the solution. So our first factor enforces that the object pose that we estimate is consistent with the tactile point cloud that we estimated, the local geometry. And so basically what we can do is transform our object to our estimated pose and compute the similarity between our observed tactile point cloud and the pose of the object. Next, we can enforce non-penetration of our tool at each time step. So given our pose, we can check if any point of the object intersects with our environment and then penalize that accordingly since we know they cannot interpenetrate. And then finally, if I've observed that contact does occur, which we can estimate using our tactile predicted wrench, we add a contact kinematics factor, which enforces that the contact point estimate should lie on the surface of both the object and the environment. So if it's not on both of these surfaces, it doesn't make sense as a contact. And finally, the contact point and force that we estimate must be consistent with the observed in-hand force and torque. So what we can do is map our force and torque at the extrinsic contact into our sensor frame and compare it to our tactile inferred wrench. So now what we have constructed here is a graph, and it's a very particular type of graph known as a factor graph, which is a very well-known probabilistic graphical modeling technique. And performing estimation with this graph boils down to a sum of nonlinear least squares, and for which there exist efficient solvers that we can apply. So now, given our tactile observations at each time step, we can recover our contact representation from our tactile feedback, and then add relevant nodes and factors to our graph in order to estimate the pose and contact at the new time step. So in our experiments, we evaluate the ability of our TAC graph method to recover poses and contacts during these multi-contact trajectories. So we use several different objects, including 3 test objects, and run randomized interactions with our environment, and then run our inference pipeline. Here we'll focus on tactile-only feedback. For the evaluation, we use the average 3D distance for our pose, which transforms the object point cloud to the predicted and ground truth poses and then evaluates the average distance between corresponding points. And for contact, we'll use the Euclidean distance to the ground truth. We compare it to several baselines that use various subsets of our physical constraints. So ICP, iterative closest point, is a classical geometric-based pose estimator. Chisel is a gradients-based estimator that adds non-penetration. And then scope is a particle filter-based method with non-penetration, contact kinematics, and force balance, but doesn't use tactile geometric feedback. So we'll start by showing some qualitative examples for our method. And remember here, we only have tactile feedback. So before making any contact, the locality of our tactile sensor means we cannot uniquely resolve the pose. So you can see that our predicted pose in yellow does not perfectly align with the ground truth in green. However, we can see that both would have very similar local tactile signatures. So it's only once we then go and make contact and we can add our additional constraints that enforce the consistency with the extrinsic contact and non-penetration that we can then actually fully resolve the pose of the object. And you can also see the predicted and ground truth contacts in purple and red. And we can also see that as I continue to make multiple contacts here, our estimate continues to improve. So quantitatively, our method shows strong performance in the tactile-only setup. So across all of our methods, across all of our testing objects here, our method performed best. And methods that cannot utilize extrinsic contact show high errors as they have no mechanism to address the locality of the tactile feedback. Scope, which can use extrinsic contact, performs the most comparably, but the lack of geometric consistency in the solver yields higher error. Similarly, we found our method has the best overall contact estimation because we can combine estimating both the contact point with the pose of the object jointly. Now we can utilize our algorithm for a downstream behavior. So here we've set up an experiment where I performed a set of exploratory pokes to localize the object from tactile feedback. I then have the robot attempt an open loop insertion with a tight tolerance. So first we'll show qualitative comparisons of the final pose and contact estimates for each method. So again, we can see that our geometric-based methods here are not able to exploit the contact and overcome the locality of the tactile. The two methods that can use the extrinsic contact do better, but multi-scope has more rotational error because it cannot incorporate the geometric feedback. And as such, during when we actually perform the insertion with our pose estimates, we see that TACGraph, our method, is the only one that's able to successfully insert the object into the fixture. So we repeat this across 4 different objects, and we find that overall TACGraph achieved the most reliable performance with an over 50% improvement on the second best method. So in this chapter, we've shown that our contact representation enables us to enforce several physical constraints on our solution that can help us address the locality of tactile feedback during prehensile reasoning. And again, this does come, of course, at the cost of several assumptions about knowing the object properties and geometries, as well as the assumption that there's no slip. Okay, now we'll move on to chapter 5, our last chapter on tactile annotated vision language action models. So far we've focused on single scenario solutions. So designing contact representations and estimation algorithms that largely focus on a single task at a time. In this chapter, we'll switch our focus to investigating if we can design contact representations applicable to multitask behaviors, in particular building on the recent wave of vision language action models. So vision language action models, or VLAs, are a nascent method for multitask language conditioned visuomotor policies. This means a single policy is designed that can be applied to multiple tasks using language to specify the desired behaviors. So for example, here is a state-of-the-art VLA here that's able to perform stowing, cleaning, and general household tasks all with a single policy. And these build off of the recent trends in machine learning that utilize internet scale text and vision data to design large scale models and extending that to the robotics realm. So these VLAs are trained via multitask behavior cloning. What that means is we have access to a large multitask data set of demonstrated behaviors where robots are teleoperated by humans to perform a variety of tasks. And then the VLA is trained to map from a given observation to the action that the human demonstrator provided. In particular, the inputs to the VLA, to standard VLAs, are generally multi-view RGB images of the scene and the robot state, along with a language-specified task goal. And from this, a network is then trained to predict an action chunk, which is a short horizon of actions that the robot should take next. And these models tend to be trained on the back of vision language models, which are pre-trained on internet scale text and language data, or sorry, text and visual data to provide language and visual reasoning to the robot. So while this has demonstrated very impressive multitask performance, the focus for these methods has primarily been on spatial, visual, and semantic variations, with less of an emphasis on physical reasoning or forceful tasks. And additionally, most demonstrated behaviors do not come with any tactile feedback, which makes it hard to incorporate that. So in this final chapter, we'll investigate how to bridge multitask VLA models with contact reasoning through tactile sensors. And in particular, we'll propose a visual annotation-based representation that provides tactile reasoning while limiting data distribution shifts from pre-trained policies. So several works have started investigating how we can bridge VLAs with tactile feedback. First, some work trains a new model from scratch to take in the tactile modality along with vision, language, and state. However, training from scratch forgoes any policy pre-training available from existing VLAs. Other methods fine-tune from an existing VLA, adding in the new modality at fine-tune time. However, this generally requires architectural changes and results in a data distribution shift from the pre-training. So to try and incorporate more robust cross-modal reasoning, several methods add auxiliary losses during this training, such as cross-modal contrastive terms. However, they still require architectural changes here and still induce distributional shifts and tend to rely on large-scale tactile data sets that are not yet readily available or scaled up to the same size as vision or text data. So in our work, we propose a method that requires no architectural changes and seeks to minimize the distributional shift in the data. So we assume we have multi-view RGB images from our robot, as well as tactile feedback from a parallel gripper. From our vision-based feedback, tactile feedback, we extract shear fields by tracking the optical flow of points on the image. And this is a simple indicator of the sorts of forces undergoing that they're acting on the robot. We then downsample these shears and then annotate them directly spatially into the visual feedback of the robot. And these annotated images then replace the original RGB inputs to the VLA along with the original language task specification and robot state. And the result here is a simple, spatially grounded and interpretable representation that incurs very little computational overhead and requires no architectural changes. So we test our proposed method across 3 tasks that focus on various forms of physical reasoning. First, we have what we call the medicine task, where we have a bottle here. That bottle either contains something in it or not. And the task is to reason about whether the bottle is full or empty, and then place it into the blue bin if it's empty or the orange if it's full. So this requires reasoning about the object masses through the tactile feedback. Second is a balancing task where we have this white object here where we've designed it so we can change the center of mass. And the task is to then go and be able to balance it on this other object in the scene, where failure to account for the center of mass will cause it to topple. And finally, we have a gear on peg insertion task. So we have to place this gear onto the peg. And this features heavy occlusions and requires reasoning about extrinsic context to understand misalignments. For each of these tasks, we collect 100 demonstrations via teleoperation setup, and then fine-tune a state-of-the-art VLA, replacing the original multi-view inputs with our annotated inputs. So now we'll look at some example rollouts from our policy. So in this top example, the bottle here is empty, which is not visible from visual feedback, so it should place it in the blue bin. What we can see is from our shear annotations, the policy is able to recognize this and correctly place it. In this example on the bottom, the medicine bottle here is now full. And so what we can see is a noticeable difference in the shear annotation, which again, the policy can use to drive the behavior correctly. Here on the balancing task, in this first example, the center of mass is far from the camera perspective. So we can see that this induces a torque in the shear, and the robot is able to guide its behavior accordingly to correctly place the center of mass. In this example, the center of mass has now been shifted near to the camera perspective. So we'll see the shear annotations now rotate in the other direction. And again, the robot is able to correctly place. We also notice that it uses, it can see the contact made between the object and the environment when placing, and it seems to feel that before it releases. And finally, here are 2 examples of the gear insertion task. And what we'll see is that our shears here can provide useful indications of the misalignments. So shears will either torque or be greater on one side to indicate how this object is misaligned. And the policy can use that to understand whether it's aligned or jammed and needs to take a corrective action. And there it goes. So here we show some example rollouts for our baselines. So we compare for now to 2 baselines. First is a vision-only baseline that gets no tactile feedback, just the visual data. So in this case, there's no visual feedback as to where the center of mass of this object is. And so the vision-only model has to basically guess. And what we see is it'll go and try and place the object. Also, because it can't feel contact here, it tends to struggle with placement. And then because it's not corrected for the center of mass, the whole thing falls over. In the second example, we fine-tune a VLA and naively just insert the tactile image as an additional input. Here, the medicine bottle is full. And what we see is just based on the tactile feedback, the policy seems unable to be sure, and it actually starts to oscillate between the 2 before ultimately placing it in the wrong bin. So quantitatively, for our success rates over the 3 tasks, first we noticed that on the medicine and balance tasks, the 2 baselines perform very similarly, which seems to indicate that raw tactile images are difficult for the VLA to reason about in at least how we've provided it. And also, they both perform essentially equivalent to chance because there are two choices for the medicine and three center of masses that we test for the balance case. Our method, in contrast, performs perfectly on the medicine task and greatly outperforms the baseline for balancing. On the gear task, both the methods that add tactile feedback outperform vision and perform somewhat comparatively. And overall, we see that our proposed Tableau method had the best overall performance across the three tasks. Okay, so to wrap things up, in conclusion, throughout this thesis, we've explored mechanisms for providing robots with an explicit sense of contact. We've shown that we can represent and infer contact by exploiting the relationship between deformation and contact. And then we've applied our contact representation and reasoning to enable performant downstream behaviors and reasoning, where we've shown that these representations enable the addition of physical structure to our algorithms, as well as help us unlock data-driven performance. Okay, I'll just quickly do some acknowledgements before we wrap up. So first, I'd like to acknowledge my two advisors, Nima and Dimitri. Thank you very much for taking me on as your student, for your guidance and your patience these last few years. Yeah, I've learned so much from you, and it's been a great honor to be your student. Next, I'd like to thank Ram and Jeff for taking the time and effort to be part of my committee. I've greatly enjoyed discussing my work with each of you and have really valued the feedback I've gotten. So thank you very much. Next, I'd like to highlight my collaborators, both at Michigan and at Mitsubishi, who I had the privilege to work directly with on a bunch of the research you just saw. And I'd like to thank everyone from both the Mint and ARM labs for the intellectually stimulating conversations and the debugging help these last few years. Next, to all my friends at Michigan and Utah and beyond, thank you for all the volleyball and hikes, board games, adventures, all that stuff. You guys have made the last few years a joy, so thank you very much for being a part of it with me. And finally, I'm eternally grateful to my parents and my family for always supporting and encouraging me, and to Niba for always supporting and taking care of me. So thank you all very much. And finally, thank you everyone for attending, and I'm happy to take any questions.